Let's walk through some of the fundamental operations in Git, starting from a blank empty repository that we set up from scratch and working through some commits in a C project. So I'm in my terminal and I'm going to go ahead and make a directory named git-demo and change my working directory to be git-demo. So if I were to check to be sure that I'm actually in this directory, we could use the print working directory command to see that the path that we're currently in is git-demo in our working directory. The next thing that initializes an actual Git repository in this directory is git init. And you'll see that the message tells you it's initialized a brand new Git repository. And you'll notice that the path that it gives you is ends in .git. So if we were to list the files with ls that are currently in this directory, we see that there are none there. However, if we list all files, so list all, and then I'm using the long format here, notice there is this hidden directory, and we know that it's a hidden directory because it begins with a dot. So the dot is giving it this nature that it's going to be hidden from the list command, and it's .git. And if we were to look inside of .git, we would see that there's a number of other directories and files in this repository's Git directory. These are all considered internal to the Git source code control system. This is where all of our commits and data are going to be stored when we're working locally. So I'm actually not going to do anything else with it. We're good to go. What gets stored in the .git folder is a little bit beyond our concern. The point is, though, that the files of your project are stored in a directory that's just hidden in your project's directory. And that's where all of the history is going to be stored until you push and pull from the internet. So the slide deck has some of these steps. There's one more set of steps that I think we should go ahead and do so that we can make commits without any concerns. And we'll look at how we can save these configuration settings for the long haul so that we don't have to do this in every repository or every session we use later. But we're going to update some configuration. So git config, and I never remember exactly what these are, user.email, chris@cs.unc.edu. and git config user.name, Chris Jordan, and of course, enter your own information here. You don't need to use my details here. So this will be your email and your name. Ideally, your email would match up with whatever your GitHub's email address is, but any email address that you have registered with GitHub should work if you want to associate the commits that you make on GitHub once you push your work to it. All right. So those things are being set up as configuration steps for associating this information. When we save changes, it will be attributed to us. The next thing we're going to do is add a C file, and we're going to just name this. This will be effectively a hello world style C file. You'll see that what we're going to do in the C file is just include the standard input output header, as well as set up in a main function that just prints hello world. Right, so I'm going to jump back and vim hello.c and include standard input output.h and set up an int main. So our main function is our entry point, and we're just going to printf hello world. Okay, and I'll use a new line character at the end of this. Our statements in C end in a semicolon, and we are using curly braces to surround the body of statements in our function here. We'll learn why main returns an integer later. It has to do with the program starting and stopping and how it exits the program in status codes. That's beyond our concern right now. So I've set up this C file. I would encourage you to get yours looking to be in this shape as well. And once I'm done, I'm going to just use Shift ZZ, capital ZZ, to save my changes. And if I wanted to prove to myself that I'd saved them, I can go back in and boom, I'm there. If I wanted to quit without saving in Vim, :Q is one way of doing that. All right, so we've got a C file and we've saved it. And so now in our working directory, we have a file named hello.c, and we can convince ourselves of that with listing the files in the directory we're working in, and boom, there it is. There's our hello.c file. Now what we're going to do, and I'm going to explain the exact steps that are going on here in just a moment. I want to get a couple of commits set up so that we can explore with a little bit more intention. But we're going to do something that you'll see is called adding a file to our staging area, and we'll talk about that in depth in just a moment. And then we're going to make our very first commit. Okay, so let's go ahead and git add hello.c and git commit m, and I'll try and be consistent with the slide deck and call this first commit. Right. So these are two commands, and one of the things that you're going to notice right off the bat is git commands. We're running the git program, or this might actually be a sequence of shell scripts under the hood that sort of dispatch off to other smaller programs. But for our purposes, it looks like we're running just the single git program, and we're giving what are called subcommands to it. So we're saying, hey git, I want you to add hello.c to an area called staging, and we'll look at staging momentarily. And then, hey git, I want you to make a commit, and the message that will be associated with that commit is the string that follows. And we see some feedback here that we've made a commit. We're working on our master branch. This was the root commit. So we do think of a repository kind of like a tree. We'll learn later it's a little bit more like a graph, but for now we can think of it as a tree. And master is just like in a master replica of a disk. It's sort of like the main copy, the primary branch that we're working on. And this is the root of our tree. And we'll talk about what this ID means. This is the ID of our commit in just a moment. And then it tells us a little bit about what went into this. So one file was changed with 6 changes, 6 insertions, 6 lines were inserted, and hello.c is what changed. If we think about this visually, what we've done is we've made a checkpoint of our project at this very point. So if we wanted to return back to where we are, we would easily be able to. What we're going to do next is add another file named readme.md, and the .md is for Markdown, which we've previously spent a little bit of time looking at. And this is a common file that you'll see in projects, and the readme file tends to tell you how to get started with the project, how to contribute to it, things like that. We're just going to add a single line, which is a comment to do everything, right? And so if I echo to do everything, if I run this command as is written here and press enter, right? Notice all echo is doing is taking its arguments, in this case, a single string argument, to do everything with a hash symbol at the front of it, and printing it back out to our standard output stream, which causes it, in this case, to show up in our terminal. Well, if we wanted to redirect that to a file named readme.md so that we actually don't send that output to the screen or our terminal, we want to instead redirect that output to a file named readme.md and save that content there. We can now see that there's a readme.markdown file in this directory, and if we were to open it in Vim, you'll notice that there's the content that we just echoed into that file. So this is not really important to Git or related to it at all, but commonly if you want to quickly set up a one-liner in a file, this is a strategy for doing so without having to open that file in Vim and back out of it and things like that. So echoing some string and then redirecting it to a file. We'll learn all about redirections in the shell very soon. Now what we're going to do is make another commit. So the same sequence of steps applies. You add a file to staging, and then when you make a commit, we form a version of our project at that point called a commit, and it's going to be linked to what came before it. So ultimately what we're going to see in our history is something that looks like this. We'll have the commit that we just made where we added this file readme.markdown, and that commit will be linked back to the one that came before it. Okay. I clear my screen just so that I can start up fresh at the top. So git add readme.md, and then git commit with a message of, let's be consistent here, add a readme file. Okay, so once again, we formed a second commit. Notice this didn't say anything about a root commit because there's only one root commit. It's the initial commit in our repository, but this time around we changed one file. We created readme.markdown. Great. Looks like we've got now 2 commits in our repository's history. And now what we're going to do is take a look a little bit more closely at staging and what it means for this history to be coming to life. As I mentioned, a commit is a snapshot of where your project was at a point in time. And it's going to contain everything that you added to that commit just before forming it. Right? And all of the data for this history is stored in that hidden.git repository. And so in the slide deck, you're going to see that when we make changes to either this history of commits or our staging area, which we're going to get into, all of that information is stored in the directory that's named .git. How that's all organized and the internal mechanisms for keeping track of everything are a little bit beyond our concerns. But as a conceptual model, you can think of this very much like a linked list. And when we're trying to illustrate that here, where we've got our commit, and the parents of this commit is referring to the one that came before it. It might seem a little bit weird to have parents be plural when we've got a linear history of commits where we're making one after the other after the other. But we're soon going to see a place where one commit can be made from merging two others, and it would have two parents. And that's what's going to make this a graph. We'll get there later on, not our concern right now. A commit is primarily going to have a link to what came before it, as well as what content was specific to that commit. And so I'm trying to illustrate that in this diagram with the blue files are going to be the files that had content specific to it in that given commit. Every commit is also going to have a message associated with it, and that's what we've been adding with the -m option when we formed the commit using add. Having been through a course in data structures, you know that there's a data structure that's a directed acyclic graph, often shortened to a DAG. Well, behind the scenes, Git is using a DAG model to represent its commit history. We'll look at how we can actually work with a DAG rather than just a linear history in a future lesson. When you don't change a file that's a part of a commit, the other files are just going to be whatever came in the previous commit or what came before it the last time they changed. So this makes commits pretty efficient. We're not making entire copies of the entire repository at a given time. What we're doing is making checkpoints where only the things that we care about and we added to that commit using the add command and committed are going to be what only the changes are what gets stored. We'll see an example of this coming up, but I want to come back to a note that's on the slide, which is you get to decide what you want to be considered important as part of a commit. So if you changed 10 files, but really only 2 of them were the ones that you wanted to add to your commit and then save and checkpoint at that point, you have the ability to do that. This means that you can have scratch files lying around, or we'll see some other kinds of files that we might not want to include in our repository. When I say it's a checkpoint in time, it's a checkpoint in time where you get to decide what's important at that given time. And so you have full control over what goes into a commit, and you have to do a little bit of work to then actually decide what goes into a commit, and that's on you as the developer. Each commit has a message, and the message is important. You really want to use informative messages, and this is crucial when you're working on real projects with teams and you're making commits that have real implications and changes. You don't want to be like, you don't want every commit message in your repository to just be next commit or fixed something or something very generic. You want to try and describe what it is that you're doing as a part of that commit. And I'm going to encourage you to try and practice that when you're working on repositories in this course. Try and describe what it is that changed since the last time you made a commit, or what's important about what you're trying to achieve, what you improved. Each commit also has the person's name and email, which we configured, and we'll take a look at later. The ID of a commit. On previous slides, I just numbered these 0, 1, 2. You could imagine a linear counting up. Well, commits have identifiers that are not just integers that count up. In fact, what they are hashes. And these hashes are hashes over the content that is in the commit, as well as the commits that came before it. And so when you form a commit, its ID is actually strongly tied to what it was that you actually committed. And we're using what's called a SHA-1 hashing algorithm to do this. If you've seen a hash table and a hashing algorithm, this is like that, but a cryptographically sound one, so that we get even more entropy here. This isn't necessarily meant to be nearly as efficient as a hashing algorithm as you would use in a hash table. But meant to be cryptographically strong, so that it would be hard to reverse engineer this. And so what each of the commits has as their identifier is a hash over the content that changed in that commit, as well as the metadata of that commit, including the message, including what was the parent, the ID of the parent that came before me. And because you're referencing the ID of the parent that came before you as part of this hash, in that parent ID was the hash of its contents, you're implicitly forming a hash over the contents of the entire history of your project up until this point. And this is a really cool feature in Git, because what it allows you to do is actually check the consistency of your data. And Git will do this behind the scenes. It will check the consistency of your data. And if even one bit goes off somewhere, you would get a different hash, and Git would know that there was some corruption in your files. And so this serves sort of a dual purpose. One, it's how we identify our commits in Git. And two, the extra cool benefit is that it ensures consistency and offers a check for consistency. You'll notice in the slide down here that I'm only referencing the first 4 digits of this hexadecimal ID. We'll learn more about hexadecimal soon. But the idea of referencing only a piece of your commit is that or a piece of your commit's ID is that these IDs are like 40 characters long, 40 hexadecimal characters long, I think. You only need to reference enough of your commit ID to uniquely identify it in your particular project's history. For the projects we're doing this semester, 4 digits should be enough. For a very real world project, 6 digits is usually enough. And so that's why I'm abbreviating it here. And you'll see when we use commands that reference IDs, we can shorten those. Okay. So this is what goes into each commit. A little bit of data about what came before you. It's a lot like a linked list, what changed, and some metadata like what was the message and who made this commit. So let's try deleting a file and recovering it and seeing just how that works. And the same process would apply to if we were to have made some changes that we wanted to revert back. We didn't want to make those changes. We accidentally deleted things, and not only did we delete some things, but we saved over our previous copy, right? So I'm going to go back to my terminal, and I'm going to remove hello.c. So that's deleting hello.c, such that if I were to look in my history here, or list the files in my directory here, if I check out, and this dash dash just is meaning reference the most recent commit, hello.c, and I list my files here again, I've got it back. All right. If I were to open hello.c and delete this line, and save my project. So now I've accidentally saved over this. We've got errors here. Oh no, this is scary. I'm going to quit out of Vim, get out of there. I can use that same command, git checkout -- hello.c. And now when I open it back up, I'm right back to where I was in the previous commit. Using the checkout command followed by the file name, you can also check out specific versions based on the commit ID. I'm going to leave that as an exercise that is easily Googleable when you need to do that. But know that this checkout, we can do it for individual files when we're working, and we'll see that we can do it for entire commits in just a moment. All right. So the big deal is, as long as we've made commits as we're making progress on our projects, we can easily revert back to those places. We're creating a sort of a proof of work, or a trail of work that we can easily get back to. So let's talk about this idea of staging that I have been waving my hands about and saying we would get to. Let's make another change, and what we're going to do is add a second line of print. We're going to print some exclamation points in our project. Right? So we're going to go into Vim, we're going to search for hello using /hello, press enter to jump to it. We're teleporting to the word hello. Then we're going to use O to insert below that line, and that'll give us a new line and put us in insert mode. We'll enter the printf with some exclamation points, and then we'll save it. All right. So I'm going to clear my screen and vim hello.c, and I used tab completion there. HE was enough to know how to autocomplete, so I just pressed tab and boom, it completed it for me. Now I'm going to use the / and type hello. Oops, these searches are case sensitive, so I should have typed /HELLO. And I jump there by pressing enter. So this was the teleporting step. I moved directly to the word I was looking for, or the line I was looking for. Alternatively, just to prove a point, I could have pressed 5 and then capital G to go to line 5, which was the line I wanted to jump to. 2 viable ways for teleporting to a specific place using Vim. I pressed the O key, and that's put me into insert mode with a brand new line. And notice that it automatically indented for me. And this would have been true if I had an if statement or a while loop and I was indented even further. So it's content aware and language aware. And let's add another print statement. Print exclamation points, and I'm going to use a \n here, even though I didn't have it in the file in the slides. Okay, so we've entered our print statement, and I'm going to go back to normal mode with control open square bracket. And previously, and I think the easiest habit is Shift ZZ for saving and quitting, but the other way is :WQ, and you'll see that commonly as well. Remember, the W is for write, the Q is for quit, and when we're using this : mode, we're using the X mode that dates way back to ed. All right, so this is a historical nod here. All right, so we've saved this file, and now we probably want to compile this and actually see if it's working. And we probably should have compiled before, but we're really focused more on the Git demo in this video than C. So we're going to use the GCC compiler here, and the G stands for GNU, and GNU stands for GNU is not Unix. It's one of those recursive acronyms that it dates back to the 80s and has to do with the open source software movement. And the CC is the C compiler. And this is the same one that you'll see in the C book. That was CC was what it was called in Unix in the early days. And then we're using a flag here, the warnings flag. We're going to enable all warnings, and we'll generally encourage you to do this through the course, so that if there's anything that C wants to complain about, or most anything, we'll see that there are some other warning flags too. It will do so, and then we're going to compile hello.c. That's going to produce a program named historically and conventionally a.out. We'll see how we can name our program something else soon. So GCC, capital W, all following the option flag, and hello.c. Boom, we've compiled our C project. If I were to list my files, we see that there's this a.out file. That's our compiled program, right? If I tried to open a.out in Vim, it would look pretty scary, right? This is a binary file. It's actually encoded to machine instructions. We're gonna get out of here quickly. So :Q, that's too scary, we gotta get out. And so now I'm gonna run this file. So /a.out is how we run a file that's a program file in the current directory we're working in. And this directory is not in our system's path. Our system's path is responsible for telling all the different directories that it's going to check to run a program. Well, we're currently working in a directory that's not on that path. So by convention, if you reference a file that we can run as a program using /, so the current directory a.out, we can run that program. And this is asking the operating system to begin this compiled program and start it up as a process, and then boom, we see that our output is there. So great, so now we've got a running program. If I list my files, we see the 3 that we're working on. So now we want to make a commit, like we've made a new meaningful version of our program. How do we think about making a commit? I mentioned this staging area. The staging area is separate from your commit history. And this is where we're going to decide what goes into the next commit. We put files and changes that we want to include in the next commit into staging first. And whenever you use the git add command, we're adding that file to staging. And staging is going to be where we sort of configure what is going to be included as our next commit. And then when we go to form a commit, that's what the commit will be made out of. Right? After you make a commit, which we did previously, your staging area clears in a way that we'll talk about in just a second. So you're starting back over on building up the next commit. We can check the current status of the staging area with get status. All right, so I'm gonna clear my screen here, and get status is a command you'll use often. It tells you a lot of things, and it tries to actually be helpful. So if you find yourself in Git in a place where you're a little bit uncertain of what to do, get status is the command I would encourage you to lean on for a little bit of guidance. So it's telling us that we're on the master branch. That's our primary branch, the master replica. And we have some stages. We have some changes that are not staged for commit. So notice that hello.c has been modified. This was the file that we've been working on. And then there's an untracked file. So a.out was the program we compiled. That was our binary file that we made from the C program. And that has never been added to a commit before. It's an untracked file. But hello.c is a file that has been tracked in Git. It has versions through the commits that we've made before. And notice that get status is telling us some things. It's telling us we can add a file, and that will add our file to staging. If we wanted to discard the changes, Git is telling us right here that exact same command we looked at before, which is we can revert those changes back to the last commit. All right, so let's add hello.c. So git add hello.c. And I'm once again going to run get status here. So this is where we started, git add hello.c, and then I ran status again. And now notice it says changes to be committed. And we've got a modification of this hello.c file, and it's changing the color coding from red before, from some uncommitted changes, to green, which is saying, hey, here are things that are being staged. So let's try and visualize this with a graphic. So status tells us that previously we had no changes to make a commit in, but we said git add hello.c, and now in this staging area, and again, the staging area is found in that hidden.git repository behind the scenes. We've added a copy of where hello.c currently is, all of its contents, to the staging area. And if we wanted to make a commit now, we could, because we've started to build up this stage. But there are a few things I want to say before we do that. We're not going to include a.out in our staging area or in our commits. And this is generally a common strategy and an encouraged strategy in source code control or version control software. For files that get built, so the programs that we generate from our source code, we tend not to include those in our repositories that contain the histories of our projects. The reason is we can always build them afresh, and sometimes the way that we build them is going to vary system to system. And if we include the built binaries, we're much more likely to have conflicts between two systems as people are working on the project. So we call a version control system for a reason. We're trying to control the versions of the source code that we're working with and the source documents. And typically we want source in the source code manager, or the SCM is another common acronym you'll see besides just VCS. So our Git source code control manager is going to have only our source files, and then the files that we produce and we build through GCC or other means, we're not going to include those in our histories so that we don't muck them up. Like, the only thing that really matters is the source knowledge, and that's contained in our source files. So we're not going to include a.out in our next commit. But what we're going to do is we're going to go ahead and make a commit. So I'm going to add a commit that's named, that has a message of another printf. And what this slide is trying to illustrate is what's happening here, and it happens all in one step. And as soon as this is done, our staging area is actually going to be clean and empty again. But here we're seeing like that intermediate moment where we take what's staged and turn it into the next commit. And part of that process is linking that commit to the one that came before it. Part of that process is generating ID and associating this metadata with it. That all happens behind the scenes for us automatically, right? So if I say git commit message is another printf, which is what we added to our repository. And you'll notice here I'm using single quotes. In Bash, there are some different implications of single quotes or double quotes, but for our purposes right now, they're both the same. So notice we made this commit, another printf, one file changed, one file was, and there's an insertion. And notice there's only one insertion. We only added one line to that file. So if I check to git status again, notice that there's no files for us to commit, but there is this untracked file a.out still, but everything else is cleaned out, right? When there are files like a.out that you know that you're going to be producing all the time in a project and you want them to be ignored by Git, there's a special file we can add the names of files we want to be ignored to called gitignore. We're going to look at that in just a moment. So when we checked status just now, we would see that the staging area is empty and we still have this a.out file that isn't part of our history, right? That's not at all included in this history of commits. But now we have 3 commits in our history. Right? By default, as I've mentioned before, the branch that Git sets up out of the gates is called the master branch, named after the idea of a master replica, where this is sort of the branch that all other branches descend from. And here, we're saying that what a branch actually is in Git, and this is an important distinction, and something you're going to be expected to know very soon. A branch is really just a reference to a specific ID. It's almost like a variable that's being set to some value, and that value is going to be the ID that you're currently working on. So here we're saying master is the branch that refers to the ID 51AD. That's not going to be the exact same ID as the commit I just made, because the time that commit was different, or your commits because your author is going to be different. So we're going to have different commit IDs based on that different data going into our commits. But the point is, master is going to be a label or a reference that's associated with a specific commit ID, right? Let's take a look at the log of commits we've made, and we're going to use a special format that puts each commit on one line. So I'm going to clear my screen one more time and git log -- one line. And so notice here are our 3 commits, the 3 messages. Here are the IDs in the left-hand side here. These are the beginnings of each ID, only the first, looks like 3, 4, 7 characters of each ID. And here, we're saying the master branch is currently referring to this commit, right? And there's a special additional reference called the head, right? And we should talk about what the head of a Git repository is. Just like how a linked list has a head reference that keeps track of, if I add another element or item to this list, the head is going to need to be updated. If we wanted to put it at the very front of a list, the head is going to need to be updated and pushed forward to refer to the next thing that gets added to it. The head in a Git repository refers to the current branch you're working on. It can also refer to an ID if we were to check out and go back in time in ID, but that's a special weird place that will come back to how we get out of that place and how we solve that place. It's kind of scary. It's called a detached head state. When you see that for the first time, you're like, what's happening? But it's okay. A head can become detached when it no longer refers to a branch, an active branch. And all we'll just do is set up a new branch in that case. We haven't even seen how to make a new branch, and we'll look at that in just a moment. But the idea of what is our head, it's the branch we're currently working on. That's what you want the head of a Git repository to refer to, the branch you're currently working on. All right, and so that's a reference to a branch. And we'll see that once we have many branches, you can jump around by checking out other branches, and your head will move to point to whatever branch you're checking out. So let's actually try listing our branches and making a new one. I'm going to show you the 2-step way of making a new branch and checking it out, as well as the 1-step and more preferred and commonly used way. So if we list git branch, what we'll see is we only have one branch in our project currently. All right. So if we give a command git branch, and let's see, we haven't done this yet. Let's just make a silly name for a branch like foobar. Terrible name for a branch. Never name a branch foobar. But by giving a name of a branch just after it, you're creating a new branch. So if we were to list our branches, you'll notice that now we have branch foobar and branch master. But notice that there's the asterisk and the color coding on master, which indicates that our head is still working on the master branch. If we were to git checkout foobar, we get a message saying, hey, you've switched your branch to foobar. And if we were to now use the get branch command again, what you'll see is we're saying we're on the foobar branch. We're no longer on the master branch. As we'll see in just a moment, both of these, and actually with git log, one line, I can show you this. We can see that both foobar and master are just referring to the ID or the git commit with ID 8FOC on my machine, and yours is going to be different. So these are just two labels for the same thing right now. We haven't made any new commits that would cause them to be different, and we'll look at what happens when we do in just a moment. For now, I'm going to check out master again. And when we go to make the branch that we're going to actually work on, I'll show you the one-line trick for doing this. And it's in the slide deck as well. So git checkout -b with a name is going to take both of those steps we did, make a new branch and check it out, and have them both happen at once. This is what I would encourage you trying to remember because it's what's most commonly used. Right? When you check out a branch, the contents of that branch are going to be updated to fill your working directory. So your working directory is going to contain whatever the state of that branch was at the last commit. Because we made two of the same, there's no difference. And right now, there's no difference between them. We'll see how we can jump back and forth between two different versions of our project in just a moment. So let's make a branch named feature. All right, so here in this example, we see that we're going to have head on our feature branch. So I'm going to use that other syntax, git checkout -b feature. Oftentimes, people will name features that they're working on or branches for features that they're working on, feature dash, and then some description of what the feature is. When you want to work on a feature and play around with it, checking out a branch just like this is how you're encouraged to do it. So now if I were to use git branch, we'll see that, of course, we're on the feature branch. We just did both of those steps at once. We created a new branch and checked it out. All right. So next, we are going to add to the .gitignore file, which is a hidden file that's going to list the files we want Git to ignore so that they don't get added to the repository's history and they don't show up when we do git status. And we're once again going to use the trick echo a.out. So the file that we're trying to ignore is a.out. So we're going to say echo a.out. And we're going to redirect this to .gitignore. Right? And so now if I run git status, notice that we have a new untracked file, this gitignore file. And this is a plain text file that on each line, it's going to contain either the name of a file or a pattern for names of files we want Git to ignore. So it doesn't show up in status and we don't add them if we add a whole directory at a time. And so that's great. Notice we don't see anymore a.out showing up on status. It's not like a file that's suggested to be worried about like this, hey, you've got this file that's new and there's changes to it. Are you sure you don't want to add it to your project? By virtue of putting a.out in .gitignore, it's getting ignored. Okay. So let's make one more change to hello.c. What we're going to do is add a print. We're going to print the word wow on a new line. So I'm going to clear and open vim hello.c. So I'm once again going to do / search for hello with a capital H, enter, boom. Could have done 5G. That would have been quicker in this case. O, notice it brings us to a new line, tabs us in, printf, and wow, \n. All right, control open square bracket, and then I'm gonna save this. So I've added one more print statement, the print statement wow. One of the things that's actually, before I close this, there's something just popped up that I wanna explain. And you'll see this happening in VS Code too, and in other modern editors. Notice this little plus symbol over here. That's actually related to Git. And that plus symbol is saying this isn't a line that you've added to your Git repository since the last time you made a commit. If I deleted a line, let's see, if I deleted a line like this, there's not going to be a good way of indicating a line deletion here. But in some cases, you'll see like here, actually, this is a line change. So this isn't a new line. It's like we changed the previous line, right? So this gutter is going to have indicators of, let me save this one more time. It's going to update every so often. And it's going to try and give you a visual indicator of what's changed since your last commit. All right, so we do that. Now I make this program again, so gcc w all for all warnings and hello.c. And if I were to run a.out again, we see that we've recompiled this new program. Wow, it's great. So if I do git status, we see that we've got hello has changed and gitignore is a new file that we haven't dealt with. All right. So why don't we go ahead and make a new commit on our feature branch that has both hello.c and gitignore as a part of our staging area. All right. So I'm going to say git add hello.c, git add.gitignore. And now if we run git status, notice that it says here are the changes that are ready to be committed. There's a new file and a modified file. Right? If I were to make a commit, so git commit m, and let me just be consistent with the slide deck here. We're going to call this add.gitignore. Now we've made a commit on our feature branch. We've extended it, and we'll look at exactly what this is doing in the background. But if I were to show the git log one more time, you'll notice that the master and foobar branches still refer to the previous commit. We haven't changed anything about those. We checked out and our head was on this feature branch. We're working on this awesome feature that added the word wow to our output. We made a commit, and so now feature is on this new commit, and it's a history that's sort of diverging from master and foobar. Right? If we wanted to visualize this, this slide's getting a little bit complex, but the point is we took those two files and we formed a new commit from it. And notice that because our head was previously on feature, so if I go back one slide and we see that head, we were checked out, we're working on feature. The implication of head and what branch it refers to is that when you make a commit, the branch that head is on is going to automatically be updated to refer to that latest commit. So notice the feature branch stays with the commit that we just made because that's the head branch we're working on, right? Master stayed back where it was. If we were to check out master, we would see our old version, okay? This is the fundamental importance of what the head branch is with respect to branches, right? So what's the big idea? Well, we can, let's check these files out and go back and forth, all right? So one of the commands, the cat command concatenate, if I were to cat .gitignore and hello.c, you can add a list of files here and it will print one out after the other. So notice a.out was the contents of gitignore and hello.c was what came after it. So notice these are the contents of these two files right now. But if we git checkout master, we're switching back to the branch master. And if I were to run by pressing up twice, that same cat command again, notice that there is no such file .gitignore, and we're back to the previous version of our hello.c file. Right, so by switching branches, we checked out the master branch, and what happened was our working directory's contents were then reverted back to what was in our commit at that point in time. So on the master branch at that specific commit before we made the most recent commit. So we could see this with git log as well. So git log one line. Notice that it's going from where the head currently is and trying to trace the log backwards from there. I think if I were to add all here, we would see that not only are we going to include back the history from where we are, but all other commits as well. And you'll see that, yeah, sure enough, that feature branch is still there. But when we checked out master, we moved branches and we went back to this point in time. Well, we can check out feature, right? So boom, we switched back to the feature branch. If I wanted to use this history one more time to convince ourselves that our head moved, sure enough, it did. So this is telling us that our head is now on this feature branch. And if we now once again check the contents of our gitignore file and hello.c, notice that they're back. Like we've just moved back to that branch where we were working on those features, and all of the changes that we made are there ready for us. So you can easily jump back and forth between branches and make progress. And that's one of the big wins of using a version control system like Git. All right. So we just showed how you can jump back and forth. When you check a branch out, your working directory is going to be going to replicate what was in the branch at the last commit that was made that you just checked out. If you're at risk of overwriting some work, Git will prevent you from trying to do this. It'll say, hey, it looks like you've got some unsaved changes. you better deal with that before we allow you to check something out. Like, it's trying to prevent you from losing work is like one of the fundamental purposes of a version control system like Git. So next, what I want to show you is how we can merge two branches together. And in this case, we've got a branch this is actually a linear history, right? So this is sort of a weird merge, because what we're doing is we're just saying, hey, master, catch up with where we are. We're going to fast forward the master branch, right? It used to refer to this commit down here. And when we merge in feature, master is now going to refer to to be at the same commit as feature. So this is a special kind of merge called a fast forward. And it happens when you've got a linear history and you're on a branch. So we're going to check out master, right? And I check my branches and we see we're on master. Well, what we're trying to do is merge into master the feature branch. And how this is going to work is it's effectively just going to move the master branch forward to be exactly where feature is, because there's a linear history here. All right, so if I say git merge feature, notice what it's saying is it fast forward commit. And if we were to look at our log of one line, you'll notice that now master and feature are on the same commit. So we've merged the feature branch into the master branch. And because this was linear, a linear history, like we didn't make any additional commits to master, like these two things hadn't actually diverged. And we'll look at very soon what happens when two branches do diverge and then you want to bring them back together again. So in a case where there's a linear history, when you merge in another branch, we're just saying, okay, master is just going to be fast forwarded to move and refer to the most recent branch that you just merged in. Okay. And I shouldn't say the most recent branch. I should say the branch that you just merged in. That's the important thing here. When we said git merge feature, while we were working, while our head was on the master branch, we're saying, hey, merge in the contents of feature so that master now has all of that. And the way it does it in this scenario is, okay, well, we're actually just going to update this master label to refer to this commit ID. Remember, a branch is only a reference to a commit ID. It's nothing fancier than that. It's not a complete copy that's separate from anything else. It's just a reference to a commit ID. And what's important to realize is that when you start working in branches, you just have a history that's potentially growing in a different direction than some other branch that might also have its own history growing in a separate direction. We'll learn later how you can bring diverging branches back together again. When we're done with a branch, like we've just finished up our feature here, we're happy with it, we don't need it anymore, we can delete branches very easily. All right, so I'm going to clear my screen, git branch, delete feature. It tells us the feature branch was deleted. If I were to look at my branches again with git branch, notice it's gone. And foobar was kind of a worthless branch as well, so I might go ahead and delete it too. All right, and so now we're in a happy place where we're back on just a single branch. We merged in some work that we did prospectively, playing it out on feature branch. We're not going to be able to demonstrate pushing because we haven't set up a repository that's out on the internet like on GitHub. But the idea of when you push a branch from your repository up to the internet, say like on GitHub or some other server, what's happening is origin is going to refer to some other copy of your repository that's on the internet. And when you push a branch, what's happening is you're saying, hey, here are all of the commits that I want to push up to this other repository who has the same branch as me. And hey, Git, I want you to figure out what are the commits that actually need to be changed, that actually changed since we last synchronized with one another. And send all of those commits up such that that repository now has all of the work in my repository. So when you push your work up to GitHub, you're pushing a specific branch of work. And effectively, after the push, that repository now has a complete copy of that branch. So these are some of the fundamental operations that you'll see in Git. We will soon look through the diverging histories, some of the more advanced techniques that you can do. But if all you take away from this is how to make commits in a linear history and how to work on, if you wanted to try some feature out that might involve a lot of changes to a lot of other files, it might be a little bit risky. If you make a branch, work in that branch, and then decide, hey, do I want to keep this? In which case, go back to your master branch and merge it in. Or if you don't want to keep it, go back to your master branch and delete it, right? And that's a key workflow in getting used to when working with Git. Great work.